Hey friends, I'm Shaptarshi. I just completed my Masters in Chemistry from IIT Kanpur. And in this video series for IIT-JAM exam, I wanted to cover all the different types of numerical problems that come for physical chemistry. And by doing those problems, I'll be explaining the concepts as well. In physical chemistry IIT-JAM, 90% of your questions will be numerical based. So it's very important. And just like this video, I'll be making similar videos on different physical chemistry topics as well. So with that, let's get started with this one.
Friends, hope you guys are doing fine, and in this we will look at, for the thermodynamics first law, all the important concepts and equations which are very important. Thermodynamics will hold a lot of marks in your IIT-JAM exam. So first of all, the most important thing are the processes, different processes that happen and the effects that cause. I'll take a different color pen. For an isothermal process, as we see, the temperature remains constant, so the change in temperature is 0. So del H, the change in enthalpy or the change in internal energy, will also be 0 in those cases. Why? Because we know this formula, and we will come to this formula later on, because there are so many formulas, but I want to tell you guys this, that NCV dt, and this is like NCV dt. So if the change in temperature is 0, the dt part is 0, because of which the del H and del U will be 0 for an isothermal process. For isobaric process, we know the pressure change, that will be like 0. For isochoric process, the change in volume will be 0, because of which your work will be 0, because we know work, the formula is minus P and dV, and you have to like take an integration of that. And for an adiabatic process, the change in heat is 0, because your change in entropy depends on that. It's the formula for that, it's Q by T, the change in heat by the temperature, right? So if the del Q is 0, so del S will also be 0. For a cyclic process, all state functions are 0. That means your del U is 0, del H is 0, and all other state functions will be 0. For a reversible process, your del S will be 0, the change in entropy. Okay, so these things are very important. These will be asked in numericals definitely. Like these, I have seen so many problems with this. We will look at problems also. So let us come to the work right now. So work, we know it can be reversible or irreversible, and for reversible I have given the formula. It can be in the volume form and the pressure form. Do note both the forms. There's just a small difference, V2 by V1 and P1 by P2, as we know from the before laws. And so just know both the forms, whichever is used. And for the irreversible process, we have this constant pressure and the change in volume. This is very important, that the reversible process, the amount of work done for reversible process is more than it is for irreversible process, right? And some conventions that you guys might be knowing, many people get confused about these conventions, is that the heat or work done on the system is positive and heat or work done by system is negative. I think in physics the rule becomes opposite, but how you remember in chemistry is that this heat or work is a selfish person. Okay, so if something is done on that person, it is positive. If something has to be done by that person, it's negative. Okay, so just make some mental note of how to remember it, because many people get confused what to write in that exam. First law is, as you guys know, del E equal to Q plus W, and so over here some important equations I am writing. Your relation between change in enthalpy del H and the change in internal energy, and how the relation looks like. This is the equation, right? The relation between change in enthalpy, and what happens in these cases, they will give an equation. Okay, suppose like Nx plus My will give you your NMO. Suppose O or something, another number is over here, like OP. So this is a number, M is a number, N is a number, and they have to say, like, they have not given the pressure and the volume, they have given the temperature. So for that you have to use this part, that P del V is also equal to del N RT. Very important to note is that del N is only for gaseous substances. So if there is a substance which is not gaseous, it's a liquid, we will not consider that. It's only for the gaseous substances. So we will come and look at the problems in the next part, but if you don't know these concepts, how will you solve the problems, right? So, and let us come to this heat capacity thing. First of all, let us look at this thing of specific heat capacity. So in the specific heat capacity, it is nothing but it is the amount of heat required to raise the temperature of unit mass, right? It's for unit mass. That's why we have this M in the denominator, by a temperature of like dT, you can say, and dT. So because it's unit mass, and if the mass of the substance is m, So that's why you have to divide it by m, because it is only for unit mass. But for molar heat capacity, all these CV, Cp, these are all molar heat capacity, constant volume, constant pressure, it's molar heat capacity, right? And so for that we can have this constant volume, that's why we have Cv. For constant pressure we have Cp, and only difference is for Cv we are taking the your change in internal energy, and for Cp we take the change in your enthalpy. So remember these two differences, and internal energy or enthalpy, right? And depending on these equations only we are getting this, right? From these equations we are getting these forms, which I previously told you that in isothermal process del U will be 0 and del H will be 0, and this formula all you guys know, that Cp minus Cv is equal to R. So I just told about specific heat capacity because sometimes they won't give the molar heat capacity, they will give a specific heat capacity, and they will give you the mass is suppose 15 gram, right? So then to find specific capacity, it is same as your molar heat capacity, just the difference is you have to divide by 15 as well, right? We will look into some problems in the next video as well, but know this concept and we will apply this concept in the next video. And so another equation between the relation, this is very famous equation as you guys know about Gibbs free energy. So Gibbs free energy and your change in enthalpy as well. So for this we have this equation and your Helmholtz free energy and your internal energy equation. So for that we have this equation. Do remember two things over here which are very important, that del G is also called your maximum non-PV work, maximum non-PV work, and your del A, the change in Helmholtz energy, that is also called as your maximum reversible work. And so these two things, sometimes they won't give the name of the Helmholtz or Gibbs free energy, they will just say maximum reversible work or maximum non-PV work. So from that you have to need to know what it is, right? And del G is also a criteria of spontaneity, and it is 0 in the equilibrium cases, and for spontaneous process it is negative. You guys know this, I know. Relation between del G and the equilibrium constant, there's one difference which you guys should know, is that del G is over here defined in the standard state. That means at 298 Kelvin and 1 atmosphere pressure. Someone asked me about this STP and NTP and SATP. I will make a video separately on that, and a video like covering all the different units of in the different like some constant in different units like R, all the different unit values which you need to use, when you need to use, and some other constants like that as well, right? For thermochemistry problems, these forms are the main forms, that del G, the change in Gibbs free energy for thermochemical equation, is the sum of standard free energy of formation of products minus the sum of standard free energy of formation of reactants, right? So this is just written in the mathematical form over here, and you need to know that the standard Gibbs free energy of formation, F means formation, for an element is 0 by convention. We will look into some problems relating to this also in the next video, and it is the same with enthalpy, right? If you have to find the change in enthalpy for a reaction, so it will be the product side minus the reactant side, and also the convention for del H also is 0, that for an element of the heat of formation is considered 0. And now in the first law, another important thing we have is the reversible adiabatic expansion. For that we have this formula of PV to the power of gamma equals to constant, where gamma is our Cp by Cv, and using our ideal gas equation we can get these two equations from our first equation. Just replace P by RT by V or that, and you will get these two equations. And for the work done in this reversible adiabatic expansion is given by this formula. We will look into the problems related to this also in the next video, right? Because if in one video if I do everything it will be very long. And so 1 by gamma minus 1, and this is totally derived, okay, this is totally derived, but I'm just telling you because derivations you might not need to know right at the end, but if you know the formula and how it's done and solve some problems relating to it, you will be able to do it in the exam as well. A very important concept in this comes in this first law part is that it's a PV graph for your adiabatic process and your isothermal process, right? And what happens over here is the slope for your adiabatic process is higher than your slope for the isothermal process, or you can say that the adiabatic process, the curve is steeper. The curve is steeper. It's very important information. It's asked many a times than the isothermal process. A comparison between the adiabatic process and the isothermal process. And from this only we'll come to the second law also. That also make a video also. And this part is one of the most important parts about the Joule-Thomson effect. because it's an application of this first law, right? So what happens in short, I'm saying what the concept of Joule-Thomson is, when we pass a gas which is more compressed, suppose it's in P1 form and it goes to P2, and in going from P1 to P2 it's expanding, so it's going from a more compressed place to a less compressed place, and it's going through a porous plug. So if a gas is passing like that, there is a change in temperature that's noted, and it is an adiabatic expansion process. Adiabatic means no change in heat, and it's expanding, right? It's also an isoenthalpy process. What is enthalpy? Like del H is your constant, and so when the gas is passing from this more compressed place to a more expanded place, right? So there's a change in temperature. Now this change in temperature is heating or cooling. So that is where this concept of inversion temperature comes up, where if the temperature is above this inversion temperature, the heating is observed. If the temperature is below the inversion temperature, cooling is observed. Cooling is observed for most gases except hydrogen and helium, which show heating, right? A formula for this inversion temperature, which you should be knowing, is Ti equals to 2A by Rv, where A and V are the van der Waals constants, right? And the Joule-Thomson coefficient mu is given by change in temperature by change in pressure at constant enthalpy Y, because it's an isothalpic process, as I said before. And some cases relating to it is that for an ideal case, the Joule-Thomson coefficient is 0 because there's no heating, no cooling, right? But for an real gas, there's it can be more than 0 or less than 0. If it is more than 0, cooling is observed. If it is less than 0, heating is observed. Why? Because see, the change in pressure is going from more compressed to less compressed. It's going from, what did I say? It's P2 to P1, I believe, right? It's going from P1 to P2 and P1 to P2, and this is like more expanded. This is your this has more pressure, this has less pressure. So it's going from a more compressed place to a more expanded place, right? So the change in pressure is decreasing. Therefore, if I write del P is negative, and if our del T is negative, that is a cooling is observed. So both of these terms will be, numerator and denominator will be negative, because of which your mu Joule-Thomson coefficient will be positive. It will be more than 0 right over here. The change in pressure is always negative because it's going from more compressed to less compressed. But if now there's a heating observed, so because of which your change in temperature has a positive value. The final temperature is higher than the initial temperature. It has a positive value. Now the numerator is positive and the denominator is negative, right? So all in all, that will be negative. So mu will have a negative value if the heating is observed. That's for hydrogen and helium. So guys, that was like all the different cases of first law that you should be knowing, the concepts which are very, very important, guys. This video is very important. Next video I'll upload the problems for the first law, and then I'll go to the second law and upload the concepts and again the problems, right? So if you revise like this, I believe you will get a very good amount of marks. I cannot guarantee that we will get all the marks, because even no one can say what will come in the exam, but these are the most important and the crunch ideas. So, and 90% questions will be based on these things, that I can say from my experience. Okay guys, all the best. See you in the next video.